another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Now, it's no secret that at least for me and for many other Homelabbers around, one of the core technologies of Homelabbing, and in addition to Homelabbing, also cloud computing, data centers, and the like, is virtualization. Now, virtualization is basically at the core of all of these because of the stretch that you can give, the additional capabilities you can give to a single server, right? No longer do you have to have 20 physical servers to run 20 different services. You can have one server having 20 different virtual machines or containers or something like that, all on one system, so you get more efficient utilization of your resources, less power consumption. It's pretty much win-wins all around. But kind of as we alluded to there, virtual machines aren't the only technology that have virtualization to thank for paving the way for them. Similarly, like in other innovations have been enabled by virtualization, like containers, Kubernetes, and serverless computing, for example, also have virtualization to thank for their existence. So in this episode, we're basically going to kind of look at how virtualization has kind of transformed computing from enabling, resource sharing on the mainframes of old to powering modern cloud infrastructures and, more relevant to us, our Homelabs. So, but before we get into all that, let's start off with our trivia question for the week. So Chris Sawyer, the sole creator of Roller Coaster Tycoon, which was released in 1999, was exclusively written in what programming language? So what programming language was Roller Coaster Tycoon written in? And that is your trivia question for the week. So I have a pretty good cybersecurity tip for you this week, so let's roll right on into this week's cybersecurity tip. So this week's cybersecurity tip is pretty unconventional, but at the same time, it kind of makes complete sense. And that is to create controlled low-risk data leaks, which you might be thinking, why on earth would I want to leak data to would-be attackers? That sounds like a horrible thing. And you're correct, but the key here is you create controlled low-risk data leaks. In other words, you basically release data that's not really that crucial, but you do it in a controlled manner so you can basically identify and trace where these leaks are going. Because leaked data, as we kind of all know, is a gold mine for attackers because, if it has passwords in there, user credentials, personal identifiable information, all that good juicy stuff that attackers want to be able to hack you, steal your identity, and all that good stuff. But if you control what information you leak to the hackers, you can basically kind of use this against them. So if you intentionally leak, controlled data in a marked or traceable manner, you can basically monitor where this data ends up, whether that's on the dark web, the clear net, and be able to identify the potential threat actors that are interested in your organization and trying to hack you because you can trace, where that data went. So in a similar vein, before we get into the little story there, but by tracking the data that you leak, you can basically kind of gain insights to tactics and methods that are used by these threat actors in order to get a hold of your data, so you can then better protect against them using those tactics. So there are benefits to leaking your own data, if you will. But of course, the key here is low risk data, or data that you're not necessarily that concerned about the public knowing, because you're of course course, leaking it on purpose. But the example that I kind of wanted to touch on here is there was a story allegedly that someone at Apple got fired because of a similar case to what we just described here. So if you're not familiar, which I feel like you probably are, especially if you listen to the podcast, every now and then we'll talk about some Apple news. But Apple is notorious for having its info get leaked, specifically in regards to things like upcoming hardware releases. So, of course, the key thing there is like anytime there's like a new iPhone coming out, new Macs, new iPads, whatever, there's almost always a community surrounding, all this leaked info about specs and, processors and what ports it's going to have and all that good stuff. So, I mean, and you can really look no further. I mean, all you got to do is look into the Apple leak followers, I guess, fandom, if you will. I'm not exactly sure what to call it. But if you look at their Lord and Savior, Mark Gurman, that man is basically coming out with leaked info on almost a daily basis. If you get into any of the kind of like Apple leak circles, you will almost certainly hear of Mark Gurman if you haven't heard of him already. Now, in fairness to the Apple leak followers, I'm not exactly sure what the best term to describe them is, but to their credit though, Mark Gurman generally has a pretty solid track record when it comes to, his credibility when it comes to things that he says are leaks, things that he identifies. So I'm not like discrediting that at all, but it is just kind of funny. Whenever I listen to like an Apple leaks thing, they always bring up Mark Gurman, and they're like, well, he said it, so therefore it must be true, like it's the gospel or something, which I always get a little fun out of. But then again, like I said, he generally is pretty darn accurate. But anyway, we're kind of getting away from the point here. So it turns out that Apple was on to this whole leaking thing, and as the story goes, they intentionally gave different info to select employees that they were suspicious of potentially leaking their information. So then when they saw what info actually got leaked, they knew exactly who their leaker was and then took action accordingly. In that case, firing said employee. So kind of a genius move by Apple, like a 1,000 IQ move right there, like, intentionally creating controlled leaked info to identify who is leaking stuff. And the other thing that Apple has going for them is, based on reports that I've heard, work at Apple is fairly siloed in the sense that if you're working on one thing, you have no idea what other people are working on. So, for instance, from like a hardware perspective, if you're working on, say, the battery tech for the new iPhone, you have no idea what chip's going to go in there. I mean, you'll probably know that it's the next number in line, but you don't know any of the specifics. If you're working on, say, the software side, you might only know of the specific feature you're working on in relation to the operating system or the app or whatever the case may be. So my understanding is it's fairly siloed. So in that sense, it's kind of easier for Apple to kind of pinpoint, where potential leaks are coming from. But also, a lot of the leaks that come out of Apple generally come from the supply chain, where Apple doesn't have as tight of a control, which is why, generally speaking, you don't really hear many leaks from the software side of things, because it's a lot easier to crack down on those, because Apple knows exactly what team is responsible for whatever feature got leaked, so then they can kind of pinpoint down who was the potential leaker and take action. So yeah, that is your cybersecurity tip for the week, making use of controlled low-risk leaks of your data to identify. Now, of course, this is more of like a from a company perspective. Of course, that doesn't make much sense on a personal level, but like a company level, it's definitely something that I don't think is necessarily that it's kind of an unconventional thing, but I think is still a pretty good one. So that is your cybersecurity tip for the week. And before we get into all of that goodness about virtualization, let's slide right on into what nerdy stuff have I been up to this week? So, over the past couple weeks, finally got back into some much needed video game programming. And I think what the main issue was? Well, not the main issue, but one of the issues is I didn't take my own advice, because if you remember back probably a couple months ago when I was talking about kind of one of the things with personal projects is when you have time to sit down to work on a personal project, it helps to kind of lay out what you're going to work on to basically remove as much friction as possible in order to be productive. Because one thing that I've personally noticed and have been reminded of once again is if I have a goal in mind or work identified of what I want to do, it's a lot easier to jump right into it and start coding. Whereas if I have to kind of debate and figure out what I want to work on, that's just that much more friction and things end up not getting done. So over the past couple weeks, as I kind of touched on a little bit last week, I started working on basically the bag or the inventory menu or screen for the Pokemon game that I am working on. And because last week was pretty much exclusively focused on getting the graphics set up, but not actually programming them in, just getting the sprite sheet set up properly. And then this week was more focused on actually incorporating that sprite sheet into the code and actually writing the code to, allow the user to interact, with the menu and, transition things and actually get the graphics displaying on the screen and integrating that front and back end components. So this week, I integrated the bag menu portion in the options menu. So now if you actually open the options menu, you can actually click the bag option. It'll actually open that screen, whereas before it wouldn't do anything. So got the background configured, and it works for both if you're playing as a male or a female character, although that feature actually isn't implemented yet. But I did test it out, and it does work. It was actually a fairly trivial solution. Basically, I just have a variable to keep track of the offset, and then it basically, upon creation of the screen, it basically basically determines if that offset needs to be set or not, and then if that offset's set, it displays the correct bag and or background for if it's a male player or a female character. So got that all working. The other thing I got working was the kind of the transitions between each one of the bags, which was really easy because I only had to do it once because of the aforementioned offset thing. I set the offset once and then everything else just works as it normally would because of how I set up the sprite sheet and everything. So that was pretty fantastic to get working. So now you can use the arrow keys and kind of go through all the various bag menus, the headers, display properly of what actual inventory you're viewing. Now it's basically a matter of creating the actual items themselves and populating each one of the inventory lists. And then comes the additional fun part of actually integrating that into the Pokemon themselves, being able to give them items, take items away, using items and all that fun stuff. But that is definitely more to come. But now that I actually got all kind of that friction out of the way of having the sprite sheet ready to go, and I just need to work on writing the code to implement it, things have definitely been progressing a lot quicker and more efficiently because there's, like I said, less friction involved for me to just get right into the code and start going. I know what I want to work on. It's right there, and I can just jump right in and get to the fun stuff, which is, of course, writing the code. And then, of course, I did a little bit of refactoring, as you do, because usually what I've noticed with this game is I'll write some helper functions or something and put them in one file, and then as I add additional screens and whatnot, I realize I need those helper functions elsewhere too. So moving some things around, making things a little more universal, if you will, definitely has improved things. But kind of as we touched on in previous episodes, helping minimize like technical debt and stuff, is refactoring as you go is a key to minimize technical debt, because kind of as I've seen here, and I have another story too that I'm going to touch on in a little bit, is it makes it a lot easier to refactor as you go and as you notice things that need to be refactored, rather than, yeah, this is a shipped product, but everything's so spaghettified because we never, took the time to refactor things as we went. And then you could spend, who knows how long trying to refactor it. But let's be real, if you're in a corporate environment, that's never going to happen, because corporate environments want you to continue to add new features. They don't want you to waste your time. To their mind, if you're just rewriting code to do the exact same thing, but it doesn't change the performance or anything from the user perspective, they're like, "What? Why are you doing that? There's no benefit to us here." Even though in reality, you're making life so much easier for the developers to actually speed up and make new updates and new features quicker, make that implementation quicker by refactoring and making it less spaghettified and more organized. From the company perspective, if you're not improving the performance or adding features or fixing bugs, what are you doing? You're wasting time. So now, of course, that's kind of a very naive approach, a very naive view. But from if you actually abstract yourself away from the trenches of actually writing the code, it kind of makes sense, right? Because if you have no knowledge of how programming and software development works, and you hear a story or a report from one of your, like, say you're like someone high up, whether that's like a director or like a VP or something like that, and you don't really know anything about code, but you hear from one of your managers that's manages a software team, comes up to you and says, "Yeah, we spent the past 2 weeks working on some updates, but no new features have been added, no additional performance has been found. We just worked on refactoring the code." From your perspective, you're like, "Wait a minute, so you spent 2 weeks and there's been absolutely no change from the end user perspective? What are you doing? You're wasting time." Which obviously is not true, because it's kind of one of those short-term versus long-term thinkings, right? Like, if the not refactoring your code as you go is a very short-sighted view of things. Of course, if you want to look to the long-term, better code usability and maintainability down the road, of course you want to refactor as you go. But that was quite the tangent. So getting back into the other story that I wanted to touch on when it comes to refactoring, at work this week, one of my coworkers was having some issues building one of the projects that we needed to have built, and I decided to help him out a little bit. And I was looking at like the build tool that was in used to essentially create the solution in order to build a project. And it was, you guys know well enough at this point that I love automation. And this build tool thing was essentially the exact opposite of automation. You had to manually enter basically every single one of the things that the build chain was looking for, and it was just a royal pain in the butt. So I was like, you know what? I can't do this. I didn't rewrite it, but I basically rewrote it to the point where you basically give it one field, and then based off that one field, it'll essentially auto-populate everything for you. It makes your life so much easier. You just run the tool, enter in the one thing that you need to search for, and then it generates your solution for you, and you build it, and you're done. It's, in my opinion, it improved things dramatically. But again, that's kind of going back to one of those things of refactoring, right? Like, I spent, all that time refactoring this build system, but in reality, at the end of the day, it didn't change anything, right? It didn't make the performance any faster. Well, it made setting up faster. But from the end user perspective of the actual software that gets built, there's no change whatsoever. But from the refactor perspective, it absolutely made a huge difference. So that's kind of just some of the importance I wanted to kind of hammer home again of why refactoring is important, and you should definitely be doing it if you can as you go, because it'll save you a lot of headache and time in the long run. So with all of that kind of preamble out of the way, let's get into kind of the main topic of this episode, which is virtualization. So we've talked many times on the podcast about virtualization and how awesome it is. But where does it come from? Because it's not like just one day out of the blue, virtualization existed, right? So when it comes to virtualization, of course, there's a couple of various components to it, but kind of the main things when you think of virtualization is virtual machines and hypervisors. Those are kind of the two big ones that play a role. And then, of course, containers and kind of build off of the idea of virtualization. But at the core of virtualization is basically virtual machines and hypervisors. And as we'll kind of get into in a little bit, there's basically two types of hypervisors. We've also talked about this before. You have your type 1 hypervisors and your type 2 hypervisors. Your type 1 hypervisors are basically bare metal. It gives the virtual machines bare metal access to the hardware, whereas type 2 hypervisors are being built above the operating system layer. So there's kind of more separation between the virtual machine and the actual hardware itself, and you kind of virtualize interfaces. So when it comes to performance, though, virtual machines running on a type 1 hypervisor are always going to be much more performant than virtual machines running on a type 2 hypervisor. And then, of course, you get into things like containers, and those are kind of like virtual machines, except a lot more lightweight and stripped down. They have their use cases as well. But, of course, all these technologies are very crucial when it comes to not only Homelabs, but also cloud computing and enterprise environments as a whole. But if we trace back the origins of virtualization, you can kind of trace it all the way back to the very early days of the mainframes. So if you're not old enough to remember the mainframes, essentially the mainframe was a large-scale computer that was, around kind of in like the 60s. It basically took up an entire room. So you can kind of think of what quantum computers are today. That's basically what mainframes were back in the day. Only like the most, pristine like universities and like government organizations or companies would be able to have them. They were absolutely massive. They took up a ton of room, and they weren't exactly practical for like everyday computing type tasks. But one of the kind of issues with mainframes was, one, they were insanely expensive, but two, resource utilization was kind of a tricky thing, because unlike today where you'll have a laptop computer that has 4 cores, 8 cores, 16 cores, has all these different cores to run programs in parallel, mainframes didn't have that. And even back to the early days of computing, computers typically only had a single core, or essentially you could only run one, instruction or one process at a time. So that's obviously not very efficient, especially if you're trying to have a bunch of people use the mainframe at the same time, or if you kind of even go a little more modern, use, multiple programs running at the same time. If you only have one core, you can only run one thing at a time. So that, of course, was a problem. But kind of an innovation came about with this idea of time sharing. So essentially what time sharing is in a nutshell is it basically allows multiple users to be able to share the same compute power of a single mainframe or a single computer core or whatever the case may be. So specifically in mainframes, essentially, if you and 20 other people all wanted to run your programs at the same time, originally it was, okay, everyone gets put in a queue, the first program runs, and then it waits for it to finish, and then it goes to the next one, waits for it to finish, goes to the next one, and so on. But of course, that's probably not the most efficient way to do things, because, for instance, if your program needs to take like user input or something, or has some other kind of blocking call, it doesn't make sense to wait for that when you have all these other jobs waiting in the queue. So that's kind of where this idea of time sharing comes in, and basically allowed you to, work on one program and then kind of be able to hop between programs and work on the execution and kind of share the resources between the various programs. And I mean, this was huge when it came to computing, and it was even, utilized, this idea of kind of time sharing, to give the illusion of, kind of a concurrency, if you will, kind of giving the illusion of that by essentially, running a set of instructions on one program until you get to like a system interrupt, and then switching to another program, running again till you get to a system interrupt, and essentially like hopping between all the various different programs, running like a few of the instructions at a time until you get to kind of like a breakpoint, if you will. And being ordered to essentially run all of these processes at the same time to essentially keep the computer always doing work, so you don't have any kind of downtime, if you will. Because, of course, if you have, a singular mainframe and you have a lot of people that want to use it at the same time, the last thing you want is for it just to be sitting there doing nothing when you have all these people waiting for their job to be completed. So that's kind of why this idea of time sharing was so huge when it came to the early days of computing. But then when you kind of move into, the 70s to the 90s, kind of when the personal computer kind of came around, this idea of virtualization and time sharing with a single, big server or mainframe, if you will, kind of sort of went by the wayside in a sense. Because back, in the 70s and early 90s and through the 90s, you didn't necessarily have you didn't really have the need per se of a bunch of programs to all be running at the same time on a personal computer. Because usually, like, if you think back to like the DOS days, of course you'd have the command prompt, right? And then when you'd want to run a command, you were essentially wanting one program at a time. You generally weren't running multiple programs at the same time, so this idea of kind of sharing CPU resource time wasn't necessarily as big of a deal. But then come like the late 90s, VMware comes along, a little company that you may or may not have heard of, VMware. In 1998, they kind of pioneered this idea of virtualization and, essentially developing a hypervisor in order to be able to run multiple operating systems on a single machine, which of course is known as a hypervisor. And kind of as we touched on before, there's two main types of hypervisors. Of course, you have your bare metal hypervisors or your type 1 hypervisors. These are like your VMware ESXi, your Hyper-V, your KVM. Those are kind of like your bare metal ones. And then, of course, you have the type 2 hypervisors, which this is like your VMware Workstation or VMware Fusion or VirtualBox. And this kind of really changed things because, as we kind of mentioned, if you can use a single computer to do, or run multiple operating systems or multiple services at the same time, it saves not only space and resources and power, but it also uses the components a lot more efficiently, right? Because there was, I just today, I think Craft Computing had a video where he was talking about the new like Xeon server or something that came out. But the point here is like the study or so that he referenced was that in cloud computing environments, with like virtualization and stuff, the average CPU utilization is between, I think, like 30 and 70% on average or something like that. And that, of course, is kind of a big deal because if you didn't have virtualization and you had to have a single server for all of the services that, users wanted to run, your average utilization would probably be a lot lower than that, right? Because anyone that's run a home lab knows the majority of the time your, individual virtual machines probably aren't really doing anything. Now you'll probably, of course you'll have different like load spikes and stuff, so you need to take that into account. But the kind of the point of virtualization is making the most use out of the resources that you have. Kind of like back in the mainframe days, if you have this massive mainframe, a lot of people want to use it, kind of like, today with cloud computing, a lot of people want to use the cloud. But some people's things that run in the cloud aren't necessarily all that demanding. You don't want the person's service that isn't all that demanding hogging up tons and tons of resources without it actually doing anything. So the more, virtual machines and more services you can kind of cram all into one server through virtualization, the better use you can make, the more efficiently you can use the resources in each one of your servers, and, be running kind of more kind of in line of that like 30 to 60% kind of sweet spot. Because the thing that you don't want to have happen is you don't want to be oversubscribed to the point where, everyone's trying to hit you all at once and you don't have enough resources to handle all of that, and, everyone's performance tanks. But you also don't want to have the opposite of that, where nobody's doing anything and your CPU is basically idling, doing nothing, when it could be, serving other customers, right? So that's kind of one of the big drivers for why virtualization kind of became such a huge thing in the enterprise world, and kind of the importance of it, making use of all of those resources. But then, of course, as things continue to change, kind of this new revolution came around, which is, kind of this idea of containers and microservices, right? So the one thing with virtual machines, and in a way you could argue their downside, is the overhead for running a virtual machine. Because when you're running a virtual machine, you have an entire operating system in that virtual machine. So by nature, it's going to take up a lot more storage space specifically than, say, like a container would. There's the footprint required to have a virtual machine is a lot higher than a container. And generally, because of that, containers are a lot less resource dependent than virtual machines, because if you're running a virtual machine that has an entire operating system in it, your virtual machine essentially has to allocate CPU resources to running the operating system, right? So, which, if you're running a container, kind of the point of a container is to provide a more lightweight, portable environment, which basically only includes what's needed in order to make your application run, and then shares things like the kernel with the actual host that it's running on. So essentially what that means is, rather than a virtual machine that comes with its own kernel and its own, operating system and all the other bells and whistles associated with the operating system, the container doesn't have that, right? Like, in an operating system, you'll have things like drivers, for like USB and, all the various other things. But in a container, you don't really need that, right? Like, especially if your container is, providing, say, like a web service, or it's like being an HTTP server, you don't need all those other bells and whistles. So you basically just need the core components to run the web server, and then you can share, the kernel itself from the host that you're on, so you can provide a much more slimmed down, lightweight package in order to distribute around. But kind of where they both, containers and virtual machines, are very similar is the fact that, assuming you're on the same platform, you can basically package up a virtual machine and ship it around to a hypervisor of the same type, and then plug it right in and you're good to go. Similarly with like containers, you can build, say, a Docker container. I could build a Docker container on my local machine, give it to you. You could spin it up in your own Docker instance, even if you're on a different operating system, and it'll work just like it would on my machine. Which is why containers and virtual machines are so incredible, is because they can, provide this ability to have the same environment to run the code, to basically reduce the issue of, oh, it works on my machine. But the kind of the other benefit too is the isolation that comes with using containers and virtual machines, because as we've talked about on the podcast before when talking about security, isolation is key when it comes to security, because you want to ensure that your systems are basically having the bare minimum, right, to reduce your footprint, the attack surface for each one of your systems. And the nice thing about virtual machines and containers is they're basically, as the kind of the name suggests, they're isolated from one another, right? So unless you're doing some super sophisticated side channel attack, which of course have happened in the past, um, if one virtual machine cannot talk to another virtual machine on the same host unless you kind of network them together. Like you can't infect, one virtual machine and then from that jump to another one. Now, through various types of side channel attacks that have crept up in the past, there is ways that you could kind of infer, instructions in the CPU and kind of get a sense of what's going on in other virtual machines. But generally speaking, virtual machine A on host X has no idea what's going on and can't communicate directly with virtual machine B on host X. But when it comes to containers, there's kind of really two big names in the game, and those are LXC containers or Linux containers, which, in case you weren't aware, they were kind of the OG. They came before Docker did, but Docker kind of came along and kind of became mainstream. Now, personally, I prefer to use Docker mainly because that's kind of what I learned first and kind of got accustomed to, and I don't think it's all that difficult to use. But of course, I've had more experience with it. But those are kind of the two big players, is Docker and LXC. But that's kind of the big kind of key there, is the difference between virtual machines and containers. Then, of course, you get to the fun stuff with Kubernetes. Now, Kubernetes is the thing in Homelabs that it's always that thing that you find very hard to justify, because kind of the point of Kubernetes is to manage kind of more cloud like apps and kind of have a more microservice architecture and be able to scale up and scale down as demand grows. And it's kind of hard to have that use case in HomeLab because, yeah, I mean, you can do it for the sake of doing it, which there's absolutely nothing wrong with that. And I encourage everyone to do things for the sake of doing things, for, at the very least to learn. But from the actual production view of things, if you're just running a modest home lab, chances are trying to throw Kubernetes into the mix is just going to overcomplicate things for basically very minimal, if any, benefit. Now, of course, if you're working on like a cloud size scale, it'll absolutely make a benefit, which is why it's used in cloud environments, because kind of the point of Kubernetes is to manage your containerized environments at scale, and like I said, to kind of be able to dynamically grow and shrink the number of containers on the various hosts that they're on as your needs, require them. So that's kind of where this idea of, the microservice architecture comes in. I think we've talked about that a little bit in the past, but essentially kind of this idea of you have purpose-built containers in a sense that kind of have, they're very, specific. Like you don't have your entire application in a container and you kind of ship it around. Now, you absolutely could do that, but kind of the idea is you have a bunch of different containers that all work together, and you can spin up, multiple instances of, say, the API request container or the front end portion of the application, and kind of being able to dynamically grow and shrink as your needs require. So with those kind of things in mind, this is kind of where we get into the kind of cloud computing area of things, where cloud computing has kind of taken over in recent years. Now, I personally have argued that cloud computing is not the future. Now, of course, it is in the sense that I think there's definite benefit of using the cloud, but also personally, I'm more of a hybrid cloud proponent. I think the hybrid cloud is a better solution because there are some things that you just want to have hosted locally. Now, of course, I'm kind of biased in that sense because I like hosting my own things locally. I know where things are. I know who's managing the data and all that stuff, because at the end of the day, the cloud doesn't exist, right? And at the end of the day, all the cloud is somebody else's computer. You don't own it. You're just renting someone else's hardware, and who knows what they have running on that hardware under the hood. So you really don't know what's going on with what you have on the cloud. But anyway, the cloud is basically kind of built on this idea of virtualization, on this idea of containers, on the idea of Kubernetes, on the idea of kind of serverless, even though there are servers involved with serverless. But this idea of providing infrastructure as code, or essentially, this idea that you can log into the web portal and you can have access to create virtual machines, spin up services, and kind of this idea of one of the things that kind of Amazon is widely known for is kind of this pay-as-you-go model, which can be have some very drastic and potentially bank-breaking implications, depending on what happens. Because if you have it set to automatically scale as the need grows, and you out of nowhere get hit with a massive amount of traffic, money could be flying out of your wallet quite quickly, which you may or may not want. But that is one thing, that virtualization at scale and kind of with Kubernetes in tow has kind of allowed for, is this idea to be able to dynamically be flexible and account for the demand that your application requires, and be able to charge you accordingly for how much actual usage you use. Because of course, from the cloud's perspective, as we kind of already touched on already, you want to make use of the hardware you have, right? If you have data centers all across, the globe or the country, or however large of an operation you got going on, the last thing you want is for those servers in your data center to not be doing anything, because that's just wasting electricity, right? Because if your servers aren't doing anything, that means you can add more clients. And of course, more clients means more money for you, and you make more money. And of course, businesses want to make money. So that's why kind of this virtualization is so crucial in kind of the cloud environment, because you can cram a bunch more users into a single box, if you will, to be able to make use of those resources in a much more efficient manner. Now, of course, the kind of the proponent of the hybrid cloud comes into this too, because you can, of course, have your services hosted in the cloud, but you can also have services hosted locally as well. Now, personally, I would like now, of course, I'm just running a home lab. I'm on residential internet and residential power. I don't have any kind of backup generators or anything like that necessarily in place. But if you are a business and you have, access to those resources to ensure that uptime, then kind of, having more of your services hosted, locally kind of makes sense. But one of the kind of draws for the cloud is that, super high uptime that you may or may not necessarily be able to achieve if you host things locally. And that's another thing that virtualization allows, because if you cluster, virtualized hypervisors together, for instance, Proxmox does this, VMware does this through their vSphere thing. The nice thing is you can have automatic failover. So if you have kind of a central pool where your virtual machine's data is stored, the nice thing is you can take a server completely offline, and that virtual machine will automatically migrate to another server, that's in the cluster, which kind of adds to this uptime, because if you have that set up, you can take a server down, and from the user perspective, their application's still up and running and getting traffic and all that good stuff. So that's another kind of thing that virtualization gives, which is why it's also very appealing for the cloud. But also kind of bringing this back into home labbing. Of course, home labbers go above and beyond when it comes to this stuff, because let's be real, do people at their house need, these, well, I guess depending on who you are and what your home lab is, you might not have a ton of super fancy old server gear, but some of us do. And do we need all of that server gear in order to run the things we want to run? Absolutely not. Could we get away with a single computer, very modest, or even running it off our desktop computer? Probably. But where's the fun in that, right? The point of having a home lab, at least in my opinion, is to essentially recreate kind of this whole cloud-like environment, but in an environment that we control. Now, of course, a home lab can be whatever you want. We've talked about this on many occasions. You can use it for things like building out virtual networks, working with virtualization, learning, penetration testing. Of course, there's a ton of different use cases for home labbing, but personally, for me anyway, at the core of my home lab is virtualization, because personally, as I've mentioned on numerous occasions, I run Proxmox and have a cluster of servers for Proxmox. Now, I don't currently have it set up to be the baller setup, where all of my virtual machines are kind of hosted in kind of a one central location, or using something like Ceph to kind of manage the storage between all the servers. I don't have that set up because, for a couple reasons. I think one being a bandwidth between my servers is kind of one issue. The other one is I kind of never gotten around to it. Plus, I've also heard Ceph is kind of a pain, or can be a pain, but I haven't gotten to the point where all the data for virtual machines is either shared or on a centralized location, that I can take a server offline and the virtual machines will automatically migrate to a different server. I don't personally have that set up, because, quite honestly, I'm fine with taking a server offline and being without whatever services I'm hosting on there for the however long I'm working on the server. But what I have done in the past is, because I have a Proxmox cluster configured, I am able to migrate virtual machines between hypervisors, which I have done on several occasions. And the nice thing about that is, because they're in a kind of clustered environment, I can perform that migration with zero downtime. Now, of course, it's not as seamless as if that data was either shared between the servers or on a centralized location, because then the transition would be almost instantaneous, because literally all it has to do is swap over kind of the memory that's being used, because the storage is elsewhere, it's not local. But in my instance, I have to migrate not only kind of the memory associated with the virtual machine, but also the entire disk associated with the virtual machine. So it does take a little bit longer, but for my personal use case, it's not all that big of a deal. But kind of getting back to virtualization here and kind of some of the use cases, building virtual networks is another thing that you can do with virtualization. One thing that's become, I think, kind of fairly big in the past few years is kind of virtualizing networks, specifically like firewalls. Now, I know me personally, I have my pfSense firewall virtualized for a couple of different reasons. One of them being the ability to easily back it up and take snapshots of it, so I can mess with things and easily roll back changes, which is one thing that virtualization kind of, not necessarily virtualization itself offers you, but kind of hypervisors will generally offer you, is the ability to back up virtual machines and back up snapshots, and kind of take snapshots in time so you can easily roll back changes if needed. But of course, Home Lab, the point of it is to have a lab environment, to be able to tinker with these things and be able to play around with things like Kubernetes if you want to. If you're a software developer like me, spinning up virtual environments to test your code in, build code in, and all the fun stuff that comes with that. So there's a lot of good use cases that virtualization allows, specifically from the home lab perspective or from the software developer's perspective that I kind of touched on, having the ability to not have to go out and buy a new computer every time I want to test, building my code in a different operating system. I can just spin up a virtual machine real quick on my hypervisor, and then get code running and deploying in there with it fairly quickly. So that's kind of another benefit as well. Now, one thing we kind of also touched on is kind of this idea of serverless computing. Now, of course, that is a myth because, in case you didn't know, there are servers behind serverless computing. The idea that you can run programs and applications in the cloud without it actually running on a server is not true. There, of course, is a server behind it. But the idea of serverless computing is this idea, whereas if you want to get the cloud-specific term, is function as a service, because of course everything has to be as a service these days, because the service market is where all the money is, because you can rake in that consistent income, and that's what everyone wants these days. But the idea of serverless computing is to essentially completely remove the idea of virtualization from the mix, because typically in kind of more classic cloud computing, I guess you could say, even though cloud computing isn't necessarily all that old, but the idea of having to spin up a virtual machine in order to host your code, you don't do any of that, right? You essentially provide the function that you want to run in the cloud, and then the cloud provider, whether that's AWS or Google Cloud, through like Lambda, like for instance, AWS has Lambda, which is kind of their serverless architecture, if you will. Essentially what you do is you write a function that runs in this AWS Lambda, and then as your code gets hit, with traffic and stuff, the Lambda function will essentially scale as needed to account for the traffic, so you don't have to worry about any of that virtualization and managing the underlying infrastructure that runs your code. Now, of course, the benefit to this from the end user perspective is you don't necessarily have to worry about managing resources, but the caveat to that is, kind of as we touched on, this is how people can run up some extremely large cloud bills because their traffic just gets absolutely slammed, and the cloud's like, okay, I'll just scale up to handle this, and you don't have the money to pay for that scaling, and then you can potentially run into issues. But the other kind of cool thing too with virtualization is one thing that's kind of becoming big now is this idea of edge computing. And kind of the idea of edge computing is to get the compute resources as close to the user as possible. So specifically from kind of like a mobile perspective, if you're out kind of in a city and you're, communicating over, whether it's LTE or 5G or whatever, which if we're being honest, they're probably the same speed anyway, because 5G, at least in my experience, has kind of been a complete joke. I know 5G in theory is a lot faster than LTE, but almost every time I've used 5G, it's basically LTE speed-wise. I mean, there are some instances I think where 5G has been faster, but tangent aside, the point here is when you're, in a mobile, environment, your speed and latency generally isn't nearly as good as if you were on, a hardline connection, a wired Ethernet connection, right? So kind of the idea of edge computing is to bring compute resources closer to where the users are, closer to the edge, and to be able to reduce the latency as much as possible. Because if you're sending a request to the cloud to do something, you have to, who knows how many hops you have to go through, who knows where that data center is located. So in order to reduce latency as much as possible, if you can move the compute resources closer to the user, you can kind of reduce, that latency. But of course, the closer you move your resources to the user, the chances that you can have a dedicated data center there is probably pretty small, right? So what you need to do is you need to be able to as efficiently as possible, cram as much resource utilization into a small footprint as possible. And how do you do that? Well, we've been basically talking about it for the past, 30 minutes, 20 minutes, something. I don't know how long we've been talking about this. Virtualization, because you can basically have, maybe a small rack of servers somewhere in the city that will run a virtualization stack that can essentially kind of handle some of those edge computing needs right near where the users are to kind of reduce that latency and speed up response times. And of course, kind of with the rise in machine learning and everything, if you can bring some of the GPU power close to the user, can even speed up those response times even more. So kind of as to recap here, we kind of talked about not necessarily super chronologically, because kind of at the end there we kind of just merged the past decade and a half or 2 decades kind of into kind of one blob of stuff. But hopefully this kind of gave you kind of a sense of where this idea of virtualization comes from, because of course it didn't come just out of the blue, and we can honestly trace the origins of virtualization back to the days of the mainframe and the whole various time sharing algorithms that were used in order to share computational power of a single mainframe amongst all the various users of the mainframe. And actually, as a fun fact, the kind of the idea of where the terminal came from was basically it wasn't even a computer. It was just like a thing that you could communicate with the mainframe with. Little fun fact there. Should have been a trivia. Actually, you know what? That should have been the trivia question for this week, because we're talking about mainframes. It would have been really cool to kind of bring that full circle. But oh well, missed opportunity, I guess. But kind of to to wrap this up and kind of why it's important, because I hope I've made it clear through kind of these various portions that we've talked about virtualization how crucial virtualization is for not only software developers, but the cloud as a whole. And it's basically what makes the internet as we know it today possible, because without virtualization there would be a lot of compute resources doing absolutely nothing. So if you thought the amount of data centers in your area was overwhelming, just imagine if they had to build maybe like 10 or 20x that just to be able to house the one little kid that wants to run his experiment server, just to play around with cloud computing. But rather than having, a single shared CPU core and like half a gig of RAM, he's taking up an entire, Dell R650 or something like that, and all like the 64 cores and 256 gigs of RAM that's on board with, 2 terabytes of storage and a couple of NVIDIA GPUs, all to just run essentially a Hello World web app. So that is kind of why virtualization is so cool, because you can be able to scale and be able to accommodate all those users and make more efficient use of the resources that you have, and why it's also so crucial for Homelabbers, right? Because typically, Homelabbers, we like to make our money last, right? Like we like to be efficient with our money, and being able to buy a server and cram a bunch of services on it through virtualization is definitely a much better avenue than having to buy a new computer every single time we want to host a new service. Now, as cool as that may be, your wallet and your power bill might not agree with you. So that is kind of some of the reasons why virtualization is so amazing. But I would like to hear from you all. What's your experience been like with virtualization? Kind of what your thoughts are on it. What do you use it for in your home lab? How are you leveraging virtualization, whether that's in your home lab, in a cloud environment? I'd be interested to hear from you, because personally, I'm always looking at new things to host in my home lab. So if you guys have any cool projects you're using virtualization for, I would definitely be happy to hear it. But before we leave for the day, let us return to our trivia question, which unfortunately, because I was not forward thinking, it was not about terminals and mainframes. But this week's trivia question is: Chris Sawyer, the sole creator of Roller Coaster Tycoon, which was released in 1990, was written exclusively in what programming language? If you said x86 assembly, congratulations, you got this week's trivia question correct. And can we just admire the fact that this single guy wrote an entire video game in x86 assembly? I mean, props to that guy, because anyone that's gone through a computer science degree that's had to write anything in assembly, let alone x86 assembly, knows that it can be quite a bear. So writing a full-fledged video game with graphics in x86 assembly, hats off to that guy. That guy is absolutely a 10x developer for sure. Maybe even a 20 or 30x or 100x. I don't know. You'll have to let me know what your thoughts are on that. But that's going to wrap it up for this episode. So if you enjoyed it, definitely leave it a rating and review, and subscribe to the Dark Assassins podcast if you haven't done so already. And be sure to share this episode around. We kind of went into kind of the history of virtualization, which I think is kind of a fun topic, and I'm sure others will as well. So definitely be sure to share it around. And if you have any questions about this episode, or have any topics or comments or ideas for future episodes, or you just want to tell me how you use virtualization, if you're on YouTube, you can leave a comment down below, or you can shoot me an email at contact@darkassassinsinc.com. The link for that is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.